Cellulose, the most common polymer on Earth, is the source of nanocellulose, a miraculous material that is incredibly eco-friendly. The future of sustainable technology lies in nanocellulose fibers, which are hardly visible to the naked eye and only a nanometer wide. Nanocellulose has the potential to gain widespread use in numerous sectors. For industrial titans, a material that is lighter than plastic yet more durable than steel would be revolutionary. The world can be changed by nanocellulose, which is made by procedures that break down plant components at the cellular level and has properties like biodegradability, low toxicity, remarkable thermal stability, and gas barrier capabilities. How does nanocellulose work? Nanocellulose is a highly versatile, renewable nanomaterial derived from cellulose, the main structural component of plant cell walls. It is composed of nanoscale cellulose fibers with extraordinary strength, flexibility, and a very high surface area. How nanocellulose works in function and application. Structure and types. Nanocellulose works due to its nanoscale size, high surface area, and strong hydrogen bonding capacity between cellulose chains. There are three main types. Cellulose nanocrystals, rigid, rod-shaped particles with high crystallinity. Cellulose nanofibrils, long, flexible fibers with both crystalline and amorphous regions. Bacterial nanocellulose, produced by certain bacteria, extremely pure and uniform. Hydrogen bonding and mechanical strength. Nanocellulose forms dense networks of hydrogen bonds, which give it high tensile strength, stronger than steel by weight. Excellent stiffness. Lightweight properties. This makes nanocellulose ideal for reinforcing materials, for example, as a strengthener in biocomposites or packaging. High surface area and reactivity. Due to its large surface area and abundance of hydroxyl groups, nanocellulose interacts well with water and other polar substances. Can be chemically modified to bind with various molecules to create sensors, filters, or drug carriers. Barrier and film-forming properties. Nanocellulose can form tight, transparent films that block gases like oxygen while allowing water vapor to pass, making it suitable for food packaging, medical dressings, biodegradable coatings, suspension and rheological properties. In water, nanocellulose forms stable, gel-like suspensions due to entangled fibrils. This property is used to stabilize emulsions in food, cosmetics, adjust viscosity in 3D printing bioinks or paints, serve as a thickening or binding agent. Applications where nanocellulose works. Composites, reinforces plastics, rubbers, or biopolymers. Biomedical, used in wound dressings, scaffolds for tissue engineering and drug delivery. Electronics, flexible, transparent substrates for screens or sensors. Filtration, nanoscale pores trap pollutants, viruses, and particles in water and air filters. Sustainable packaging, biodegradable, oxygen barrier coatings. Nanocellulose works because of its nanoscale dimensions, high strength-to-weight ratio, surface chemistry, and ability to form strong networks. Its functionality is rooted in natural cellulose fibers, but enhanced through nanostructuring, allowing it to replace plastic, strengthen materials, clean water, and support green technologies. Nanocellulose is a natural, renewable nanomaterial derived from cellulose, which is the primary structural component found in the cell walls of plants. Cellulose itself is composed of long chains of glucose molecules linked together in a way that allows strong intermolecular hydrogen bonding. When cellulose is broken down into nanoscale fibers, typically measuring less than 100 nanometers in width, it becomes what is known as nanocellulose. Due to its extremely small size, large surface area, and unique physical properties, nanocellulose exhibits characteristics that are significantly different from regular cellulose. There are three main forms of nanocellulose, each with distinct structures and properties. The first type is cellulose nanocrystals, which are rod-shaped particles with a highly ordered crystalline structure. These are very strong and rigid. The second type is cellulose nanofibrils, which are longer, more flexible fibers composed of both crystalline and amorphous regions. CNFs are more entangled and better at forming gel-like networks. The third type is bacterial nanocellulose, which is produced by certain bacteria and is known for its exceptional purity, uniformity, and water-holding capacity. Nanocellulose works by taking advantage of its small size and the strong hydrogen bonds that form between the hydroxyl groups on its surface. These bonds give nanocellulose extremely high tensile strength and stiffness, making it stronger than steel on a weight-to-weight basis. At the same time, it is lightweight, transparent, and biodegradable. These properties allow nanocellulose to serve as a reinforcing agent in composites and other materials, improving their strength, durability, and environmental profile. The high surface area of nanocellulose also makes it highly reactive. Its surface can be chemically modified or functionalized to bind with other substances, enabling it to serve as a platform for targeted applications. For example, it can be used in drug delivery systems, biosensors, or as a binding agent in food and cosmetics. Its interaction with water is particularly important. Nanocellulose readily absorbs and holds water, forming stable suspensions or gels. These suspensions are useful in applications such as 3D printing bioinks, paints, and emulsions. Nanocellulose also has excellent barrier properties. When dried into thin films, it can create strong, transparent sheets that block oxygen and oils but allow water vapor to pass through. This makes it ideal for use in food packaging, where it can preserve freshness while remaining biodegradable and safe for the environment. Its ability to form networks and membranes also makes it suitable for high-efficiency water and air filtration systems, where it can trap contaminants at the nanoscale, including bacteria and viruses. In electronics, nanocellulose is being developed as a flexible, transparent substrate for components like displays, sensors, and batteries. Because it is lightweight, strong, and sustainable, it offers an eco-friendly alternative to plastics and metals in many devices. Additionally, in biomedical applications, nanocellulose is used in wound dressings, tissue scaffolds, and controlled drug release systems because it is biocompatible, non-toxic, and capable of maintaining a moist environment conducive to healing. Nanocellulose works by leveraging its nanoscale structure, high surface area, strong hydrogen bonding, and unique mechanical and chemical properties. It can be engineered to serve a wide variety of functions, from strengthening materials and improving barrier properties to enabling medical, electronic, and environmental technologies, while remaining sustainable, biodegradable, and derived from abundant natural sources. Can nanocellulose replace plastics? Yes, nanocellulose can replace plastics in many applications, particularly where sustainability, biodegradability, and high strength are desired. However, whether it can fully replace all types of plastics depends on the specific use case. Here's a comprehensive explanation. Where nanocellulose can replace plastics. Packaging materials. Nanocellulose is especially promising in food packaging and biodegradable containers. It can form transparent, flexible films with excellent barrier properties against oxygen and oils. This makes it ideal for food wraps and pouches, coatings for paper or cardboard, compostable trays and containers. Unlike conventional plastics like polyethylene or polypropylene, nanocellulose films are biodegradable, non-toxic, and derived from renewable resources. Plastic composites. Nanocellulose can be used as a reinforcing agent in bioplastics, polylactic acid or PLA, to improve strength and reduce the amount of petroleum-based plastic required. These nanocellulose reinforced composites can be used in automotive parts, electronics casings, sports equipment, furniture, coatings, and films. Nanocellulose can be made into thin, high-strength, water-based coatings that substitute for synthetic polymers in paper and cardboard coatings, waterproof but breathable clothing materials, protective barriers, hybrid and transitional solutions. Rather than replacing all plastics outright, nanocellulose is most effective when used to improve or reduce plastic usage, such as blending with biodegradable plastics to create stronger, eco-friendly composites, creating multi-layer films with nanocellulose as a biodegradable barrier layer, enhancing recyclability or compostability of packaging. Environmental benefits. Using nanocellulose instead of plastic offers major sustainability advantages. Derived from renewable sources, plants, agricultural waste, or bacteria. Non-toxic and biodegradable. Low environmental impact when produced sustainably. Potential for carbon-negative manufacturing if sourced from reforested or waste biomass. Nanocellulose can replace many plastics, particularly in packaging, coatings, composites, and sustainable materials. It is biodegradable, strong, lightweight, and comes from renewable resources. However, to fully replace plastics in all sectors, challenges like water sensitivity, thermal limits and cost must still be overcome. In the meantime, nanocellulose is an excellent green alternative or additive that can dramatically reduce our dependence on fossil-based plastics. Nanocellulose has strong potential to replace plastics in many applications due to its unique combination of strength, biodegradability, renewability, and environmental safety. However, whether it can completely replace all forms of plastic depends on the specific function and requirements of each application. In many cases, nanocellulose is already proving to be an effective alternative, especially in areas where environmental sustainability is a priority. One of the most promising areas where nanocellulose can replace plastics is in packaging materials. Nanocellulose can be formed into thin, transparent, flexible films that act as effective barriers against oxygen and oils. These properties make it ideal for food packaging, where it can help preserve freshness without the environmental harm associated with petroleum-based plastic films. Additionally, nanocellulose coatings can be applied to paper, cardboard, or biodegradable plastics to enhance their durability and barrier performance, enabling the creation of fully compostable packaging solutions. Nanocellulose is also being used in plastic composites, where it serves as a reinforcement material. When added to bioplastics such as polylactic acid, nanocellulose greatly improves their mechanical strength, flexibility, and durability. These nanocellulose reinforced composites can be used in a wide range of products, including car parts, electronics casings, consumer goods, and construction materials. By incorporating nanocellulose, manufacturers can reduce the amount of plastic needed, lower the carbon footprint of their products, and increase the use of renewable materials. In addition, nanocellulose works well as a coating and film material. It can be applied to surfaces to create water-based, non-toxic, and biodegradable coatings that replace synthetic polymer coatings in packaging, textiles, and even medical products. Its ability to form smooth, strong films also makes it a candidate for replacing certain types of plastic wraps and labels. Rather than replacing all plastics outright, nanocellulose is currently best used as a supplement or partial replacement. For example, it can be blended with biodegradable polymers to create high-performance, eco-friendly plastics. It can also serve as a biodegradable barrier layer in multi-layer films, replacing petroleum-based layers while maintaining overall functionality. The environmental benefits of using nanocellulose instead of conventional plastics are significant. Nanocellulose is produced from renewable plant materials or microbial sources, making it a sustainable alternative to fossil-derived plastics. It is fully biodegradable, non-toxic, and safe for use in consumer products, medical devices, and food packaging. If produced from waste biomass or sustainably managed forests, nanocellulose can even have a net negative carbon footprint, contributing to climate change mitigation. Nanocellulose can replace plastics in many areas, especially where biodegradability, strength, and sustainability are important. It is already being used in packaging, composites, coatings, and environmentally friendly materials. However, limitations such as water sensitivity, thermal instability, production costs, and compatibility with current manufacturing systems must be addressed before it can serve as a universal plastic replacement. In the meantime, nanocellulose offers a powerful way to reduce our reliance on conventional plastics and move toward a more sustainable, circular economy. What can be done with nanocellulose? Nanocellulose is an exceptionally versatile material, and a wide range of products and technologies can be developed using it due to its remarkable properties, such as high mechanical strength, biodegradability, transparency, renewability, and large surface area. A comprehensive overview of what can be done with nanocellulose across different fields. Sustainable packaging and materials. Nanocellulose can replace petroleum-based plastics in many packaging applications. Biodegradable food packaging films with excellent oxygen and oil barrier properties. Coatings for paper, cardboard, and compostable plastics to improve water resistance and durability. Transparent wrapping materials that protect food and degrade naturally in the environment. Single-use containers and cutlery made from molded nanocellulose composites. Reinforcement in composites and construction materials. Nanocellulose acts as a strong reinforcing agent in composite materials. Bioplastics reinforced with nanocellulose are stronger and lighter. Construction materials like concrete and plaster can be enhanced with nanocellulose to improve strength, durability, and reduce weight. Fiber-reinforced materials for automotive parts, furniture, and sports equipment. Water and air filtration. Nanocellulose fine fiber network and high surface area make it excellent for filtering. water purification membranes that can trap bacteria, viruses, and nanoparticles, air filters for removing dust, allergens, and fine particulate matter, PM2.5 and PM10, heavy metal removal and dye adsorption from industrial wastewater using functionalized nanocellulose, biomedical and healthcare applications. Nanocellulose is biocompatible, sterile, and safe for medical use. Wound dressings that absorb fluids while keeping wounds moist and protected. Tissue engineering scaffolds for regenerating skin, bone, or organ tissues. Drug delivery systems using nanocellulose hydrogels or carriers for controlled and targeted release. Implantable devices and prosthetics where lightweight, biocompatible materials are required. Electronics and flexible devices. Due to its mechanical strength, transparency, and flexibility, nanocellulose is a candidate for use in flexible, transparent displays and substrates for smartphones and wearable electronics. Printed circuits and conductive films, when combined with conductive materials, e.g., silver nanoparticles or carbon nanotubes. Supercapacitors and batteries as part of separators, electrodes, or flexible components. Biodegradable electronics for low-impact devices and sensors. Cosmetics, pharmaceuticals, and food. Nanocellulose is safe for ingestion and topical use, enabling applications in personal care products such as creams, gels, and lotions for stabilization and texture. Pharmaceutical tablets and capsules as a binder or disintegration agent. Food packaging and edible coatings to extend shelf life and protect freshness. Emulsion stabilizers in foods, sauces, and drinks. Textiles and smart fabrics. Nanocellulose can enhance textiles through strengthening natural or synthetic fibers while maintaining breathability. Water and flame-resistant coatings for clothing and upholstery. Smart fabrics embedded with sensing or conducting elements. 3D printing and bioinks. Nanocellulose can be made into printable gels and pastes. 3D printed biomedical implants and scaffolds for personalized medicine. Sustainable prototyping materials with minimal environmental impact. Bioinks for printing living tissues and organ models in regenerative medicine. Sensors and responsive materials. Nanocellulose can be chemically modified to detect specific substances. Environmental sensors for detecting heavy metals, toxins, or humidity. Biosensors for glucose, pathogens, or disease biomarkers. Smart labels and packaging that change color or properties based on temperature or spoilage. Environmental remediation. Nanocellulose can be functionalized to absorb pollutants. Oil spill cleanup materials that are absorbent, lightweight, and biodegradable. Carbon capture and gas separation membranes. Agricultural soil amendments to improve water retention and microbial health. Nanocellulose can be used to create a vast array of sustainable, high-performance products across industries. It can replace plastics, reinforce materials, purify water, deliver medicine, build electronics, and even support environmental cleanup. As production methods improve and costs come down, nanocellulose is expected to become a key material in building a circular, bio-based economy. Nanocellulose is an extraordinarily versatile material derived from plant-based cellulose that can be used to create a wide variety of sustainable, high-performance products across multiple industries. Its unique combination of strength, lightweight, biodegradability, high surface area, and renewability makes it suitable for replacing conventional materials like plastic, metals, and synthetic polymers in many applications. Below is a comprehensive explanation of what can be done with nanocellulose. Sustainable packaging and biodegradable materials. Nanocellulose can be used to produce biodegradable and compostable packaging materials. It forms strong, transparent films that serve as effective barriers against oxygen, oils, and some moisture. These properties make it ideal for food packaging that preserves freshness while reducing environmental pollution. Nanocellulose can also be used to coat paper, cardboard, and other biodegradable substrates to improve their mechanical strength and water resistance. As a result, it can replace petroleum-based plastics in single-use containers, food wraps, and packaging films. Reinforcement in composites and construction materials. Nanocellulose serves as a strong and lightweight reinforcement material in composites. When mixed with polymers such as polylactic acid, it significantly enhances the mechanical strength, stiffness, and durability of the final product. These nanocellulose reinforced composites can be used in automotive parts, construction panels, furniture, sports equipment, and building materials like concrete and plaster. This allows manufacturers to reduce plastic use while improving material performance and sustainability. Water and air filtration systems. Due to its fine fibrous network and high surface area, nanocellulose is an excellent material for filtration systems. It can be used to create membranes that filter out bacteria, viruses, heavy metals, microplastics, and other pollutants from water. Nanocellulose-based air filters are also effective at removing dust, allergens, and fine particulate matter from the air. These filters are biodegradable, lightweight, and efficient, offering an eco-friendly alternative to synthetic filtration media. Biomedical and healthcare applications. Nanocellulose is biocompatible, sterile, and non-toxic, which makes it highly suitable for biomedical applications. It can be used in wound dressings that absorb fluids, maintain a moist environment, and promote healing. It also serves as a scaffold for tissue engineering, helping regenerate skin, bone, or organ tissue. Additionally, nanocellulose can be engineered into drug delivery systems that provide controlled and targeted release of medication. It is also used in implantable devices and prosthetics due to its strength, safety, and compatibility with human tissue. Flexible electronics and biodegradable devices. In the field of electronics, nanocellulose is being explored as a substrate for flexible, transparent electronic components. It can be used in printed electronics, displays, sensors, and even circuit boards. When combined with conductive materials such as silver nanowires or carbon nanotubes, nanocellulose becomes electrically active while retaining its flexibility and biodegradability. These properties make it useful in wearable devices, smart packaging, and environmentally friendly electronics. Personal care products, pharmaceuticals, and food applications. Nanocellulose is safe for human use and can be incorporated into cosmetics, pharmaceuticals, and food products. In cosmetics, it helps stabilize creams, lotions, and gels and improves texture. In pharmaceuticals, it acts as a binder or disintegrant in tablets, or as a carrier for controlled drug release. In the food industry, it can be used as an emulsion stabilizer in sauces and beverages, or as an edible coating to preserve fruits and vegetables by reducing moisture loss and microbial growth. Advanced textiles and smart fabrics. Nanocellulose can be integrated into textiles to improve their strength, breathability, and functionality. It can be used to coat fibers and fabrics to make them more water-resistant, fire-retardant, or antibacterial. In smart fabrics, nanocellulose can be embedded with sensors or conductive elements to create responsive clothing that changes based on environmental conditions or user input. This opens possibilities for wearable technology and functional garments. 3D printing and bioink production. Nanocellulose can be transformed into gels and pastes that are suitable for 3D printing. These printable nanocellulose-based materials are used to fabricate customized, biodegradable objects and medical implants. In bioprinting, nanocellulose is used as a bioink for printing living tissues and organ models. Its ability to support cell growth and maintain structure makes it ideal for regenerative medicine and tissue engineering applications. Sensors and smart responsive materials. Nanocellulose can be chemically modified to detect specific substances, making it useful in sensor technology. It can be used to create biosensors for detecting glucose, pathogens, or disease markers, as well as environmental sensors that respond to pollutants, temperature, or humidity. Nanocellulose-based smart labels and packaging materials can change color or shape based on spoilage, contamination, or temperature exposure. Environmental remediation and pollution control. Nanocellulose can be functionalized to absorb pollutants from the environment. It is effective at removing oil from water, capturing heavy metals, and absorbing dyes and toxins from industrial wastewater. In environmental restoration, it can be used to clean up oil spills and support soil health. It is also being researched for use in carbon capture membranes that absorb CO2 and other greenhouse gases. Nanocellulose is a powerful, sustainable material with applications across a wide range of sectors. It can be used to replace plastics in packaging, reinforce construction materials, purify water and air, support biomedical innovations, and enable advanced electronics. Additionally, it contributes to cleaner industries, safer healthcare products, and more sustainable consumer goods. As production technologies improve and costs decrease, nanocellulose is expected to play a central role in advancing a circular, bio-based economy that minimizes environmental impact and maximizes resource efficiency. What materials can it replace as an eco-friendly and versatile alternative? Nanocellulose can replace a wide range of conventional materials due to its remarkable combination of mechanical strength, lightweight, biodegradability, renewability, and environmental safety. As an eco-friendly and versatile alternative, nanocellulose can substitute or partially replace the following materials across multiple industries. Petroleum-based plastics. Materials replaced: polyethylene, polypropylene, polyethylene terephthalate, polystyrene, polyvinyl chloride. How nanocellulose replaces them. Used in biodegradable films and coatings for food packaging, bags, and containers. Forms compostable composites when combined with biopolymers like PLA. Provides strong, flexible, and transparent alternatives to conventional plastic films. Benefits: reduces plastic pollution. Enables circular economy solutions. Derived from renewable plant sources. Paper and cardboard coatings. Materials replaced: polyethylene coatings, wax coatings, fluorochemicals used for water and grease resistance. How nanocellulose replaces them. Acts as a biodegradable barrier layer on paper and cardboard. Improves strength, oil resistance, and water resistance without toxic chemicals. Benefits: recyclable and compostable. Avoids hazardous, forever chemicals like PFAS. Suitable for food-safe and sustainable packaging. Glass fibers and synthetic reinforcements. Materials replaced: glass fiber, carbon fiber, aramid, Kevlar, talc fillers. How nanocellulose replaces them. Serves as a reinforcing agent in plastics, cement, and composites. Increases strength and reduces weight in automotive parts, building materials, and sports gear. Benefits: lower embodied energy. Non-toxic and biodegradable. Safer to handle and dispose of than synthetic fibers. Petroleum-derived thickeners and emulsifiers. Materials replaced: carbomers, synthetic polymers, silicone thickeners. How nanocellulose replaces them. Acts as a rheology modifier and stabilizer in personal care, food, and pharmaceutical products. Benefits: biocompatible and non-irritating. Provides stable, natural viscosity and texture. Safe for skin and ingestion. Biomedical polymers. Materials replaced: polyethylene glycol, polyvinyl alcohol, and synthetic scaffolds. How nanocellulose replaces them. Used in wound dressings, tissue scaffolds, and drug delivery systems. Supports tissue growth and healing due to its biocompatibility. Benefits: derived from natural sources. No cytotoxicity. Absorbs fluids and promotes healing naturally. Petroleum-based 3D printing materials. Materials replaced: ABS, PLA when derived from fossil fuels, photopolymers. How nanocellulose replaces them. Can be used as a base for eco-friendly 3D printing inks and gels. Suitable for medical implants, prototyping, and biodegradable objects. Benefits: reduced plastic waste. Printable at lower temperatures. Can be mixed with other biomaterials. Synthetic filtration media. Materials replaced: nylon filters, polyester filters, activated carbon composites. How nanocellulose replaces them. Used in membranes and filters for water purification and air filtration. Traps bacteria, viruses, dust, and micropollutants. Benefits: renewable and biodegradable. High filtration efficiency with low pressure drop. Can be composted after use. Plastic-based electronic substrates. Materials replaced: PET, polyamide, and other plastics used in flexible electronics. How nanocellulose replaces them. Serves as a transparent, flexible, and biodegradable substrate for printed electronics, sensors, and displays. Benefits: reduces e-waste. Enables development of biodegradable devices. Supports greener consumer electronics. Synthetic foams and insulation materials. Materials replaced: polyurethane foams, styrofoam, fiberglass insulation. How nanocellulose replaces them. Forms aerogels and foams with thermal insulation and shock absorption properties. Benefits: lightweight, breathable, and compostable. Reduces microplastic release in buildings and packaging. Industrial absorbents and cleanup materials. Materials replaced: polypropylene absorbents, synthetic sponges, activated carbon in some uses. How nanocellulose replaces them. Used in oil spill cleanup, pollutant capture, and wastewater treatment. Benefits: absorbs oil while repelling water. Degrades naturally without toxic residues. Made from agricultural or forestry byproducts. NanoCellulose can replace the following materials: conventional plastics, PE, PP, PET, etc., glass and carbon fibers, petroleum-based thickeners and stabilizers, synthetic coatings and water-repellent chemicals, biocompatible medical polymers, plastic-based electronic substrates, synthetic filtration media, styrofoam and insulation foams, oil absorbents, and industrial cleanup materials. NanoCellulose stands out as a clean, biodegradable, and renewable alternative. It provides similar or superior performance in strength, flexibility, and function while greatly reducing environmental impact. As such, it plays a key role in transitioning from fossil-derived materials to a circular, bio-based economy. NanoCellulose is a highly promising eco-friendly and renewable material that can serve as a versatile alternative to many conventional, non-sustainable substances used in industry and consumer products. Its unique properties, including high tensile strength, lightweight structure, biodegradability, large surface area, non-toxicity, and the ability to be derived from abundant biomass sources like wood, agricultural residues, and even algae, allow it to replace a wide variety of materials that contribute to environmental degradation. Below is a comprehensive explanation of the materials NanoCellulose can replace and how it functions as a sustainable substitute. Petroleum-based plastics. NanoCellulose can replace plastics such as polyethylene, polypropylene, polyethylene terephthalate, and polystyrene, which are commonly used in packaging, containers, films, and disposable products. When used in films, coatings, and molded items, NanoCellulose offers similar strength and flexibility, but is fully biodegradable and compostable. By combining NanoCellulose with biopolymers like polylactic acid, manufacturers can produce high-performance bioplastics that degrade naturally in the environment, thereby reducing plastic pollution and reliance on fossil fuels. Plastic coatings on paper and cardboard. In food packaging and disposable containers, paper is often coated with plastic or wax to provide water and grease resistance, making it non-recyclable. NanoCellulose can serve as a natural coating that enhances paper's durability and water resistance without impairing recyclability or compostability. This allows for the development of fully biodegradable packaging that is strong, safe for food contact, and does not release harmful chemicals when discarded. Synthetic reinforcing materials. NanoCellulose can replace synthetic reinforcing agents such as glass fiber, carbon fiber, and talc and composite materials used in automotive parts, sports equipment, construction panels, and consumer goods. When added to plastics or resins, NanoCellulose significantly increases mechanical strength, stiffness, and thermal stability. Unlike synthetic fibers, which are energy-intensive and difficult to recycle, NanoCellulose is lightweight, renewable, and can be safely degraded or reused. Industrial thickeners and emulsifiers. In cosmetics, food, and pharmaceuticals, synthetic thickeners like carbomers and polyacrylates are commonly used. NanoCellulose can serve as a natural rheology modifier, stabilizer, and thickener in lotions, gels, creams, sauces, and emulsions. It offers excellent viscosity control and emulsion stability while being skin-safe, edible, and non-toxic. This makes it ideal for personal care products and food items that are environmentally friendly and safe for sensitive applications. Medical polymers and scaffolds. Biocompatible synthetic materials such as polyethylene glycol, polyvinyl alcohol, and synthetic hydrogels are used in medical devices, implants, and tissue engineering. NanoCellulose can replace or complement these materials in wound dressings, drug delivery systems, and bioscaffolds. It supports cell growth, promotes healing, and can be modified to carry active pharmaceutical ingredients. Unlike some synthetic polymers, NanoCellulose is non-inflammatory, sterilizable, and fully biocompatible. Flexible plastic substrates in electronics. Plastics such as polyamide and PET are widely used as substrates in flexible electronic devices, displays, and printed circuits. NanoCellulose, particularly in the form of transparent cellulose nanofiber films, can be used as a flexible and biodegradable alternative. It maintains transparency, flexibility, and thermal stability while offering a sustainable solution for the growing problem of electronic waste. Synthetic filters and membranes. NanoCellulose can replace synthetic filtration materials made from polyester, nylon, and polypropylene in water and air filtration systems. Its nanoscale fiber structure makes it effective in capturing bacteria, viruses, microplastics, heavy metals, and fine particulate matter. These filters are renewable, biodegradable, and can be produced without harmful solvents or chemicals, providing an eco-friendly option for purifying air and water. Plastic-based 3D printing materials. Additive manufacturing often relies on plastic filaments such as ABS and PLA. NanoCellulose can be formulated into printable hydrogels and composites for 3D printing, allowing for the creation of biodegradable and biocompatible structures. These include custom medical implants, tissue scaffolds, packaging prototypes, and eco-friendly consumer goods, all with reduced carbon footprint and material waste. Foams and insulation materials. Styrofoam, expanded polystyrene, and polyurethane foams are commonly used for insulation, packaging, and cushioning. NanoCellulose can be made into lightweight, porous foams and aerogels that provide thermal insulation and shock absorption. These materials can be composted after use, avoiding the long-term pollution associated with synthetic foams. Industrial absorbents and cleanup products. Synthetic oil-absorbing pads and sponges used in spill response are typically made from polypropylene. NanoCellulose aerogels and sponges are excellent alternatives due to their high absorbency, low density, and biodegradability. They can be used to clean up oil spills, chemical leaks, and wastewater contaminants, then safely composted or incinerated without releasing toxic substances. NanoCellulose can replace a broad spectrum of environmentally harmful materials, including fossil fuel-based plastics, synthetic fibers, chemical thickeners, medical polymers, and plastic foams. Its applications range from packaging, construction, and automotive parts to healthcare, electronics, and environmental remediation. As an eco-friendly, biodegradable, and renewable resource, NanoCellulose offers a path toward reducing pollution, conserving natural resources, and advancing the development of sustainable circular economies. Its versatility makes it one of the most promising green materials for replacing non-renewable, polluting substances across nearly every sector of modern industry. How can we produce nanocellulose by using CO2, methane from the atmosphere, also pollution and waste? Nanocellulose can be produced sustainably by capturing and utilizing greenhouse gases such as carbon dioxide, CO2, and methane, CH4, as well as organic waste and industrial pollution. This is achieved by converting these waste streams into cellulose-rich biomass through biological or chemical processes. The biomass is then refined into nanocellulose, a highly versatile and biodegradable material with applications across nearly every industrial sector. Here is a comprehensive explanation of how each of these waste sources can be used to produce nanocellulose. Producing nanocellulose from CO2 using photosynthetic organisms. Carbon dioxide can be captured from the atmosphere or industrial emissions and used to grow photosynthetic organisms such as microalgae and cyanobacteria. These microorganisms naturally absorb CO2 during photosynthesis and convert it into biomass composed of cellulose, starch, and other valuable compounds. Some algae species, such as chlorella or Cenodesmus, are known to contain sufficient amounts of cellulose that can be extracted and refined into nanocellulose. The biomass is harvested, dried, and processed using mechanical, grinding, homogenization, chemical, acid hydrolysis, or enzymatic methods to produce nanofibrillated cellulose or cellulose nanocrystals. Producing nanocellulose from CO2 via engineered bacteria. Another method involves using bacteria that convert CO2 into acetic acid or other intermediates, which can then be fed to cellulose-producing bacteria like Gluconacidobacter xylinus. These bacteria produce bacterial cellulose, which is extremely pure and can be formed into sheets or films. The bacterial cellulose is then processed into nanocellulose using high-pressure homogenization or acid treatment. This method is advantageous because bacterial cellulose has a higher crystallinity and uniform structure compared to plant-derived cellulose. Producing nanocellulose from methane using methanotrose. Methane, a potent greenhouse gas, can also be used to produce nanocellulose indirectly. Methanotrophic bacteria consume methane and convert it into microbial biomass. Although these bacteria do not produce cellulose directly, their biomass can be used as a nutrient source for algae or cellulose-producing microbes. Alternatively, methane can be chemically transformed into methanol, formic acid, or acetic acid, which can be used as carbon sources to feed cellulose-producing organisms. Once sufficient cellulose biomass is obtained, it can be processed into nanocellulose. Producing nanocellulose from organic and agricultural waste. Agricultural residues such as straw, corn stalks, sugarcane bagasse, forestry byproducts like sawdust and wood chips, and food waste, such as fruit peels or paper waste, are rich in lignocellulosic biomass, which contains cellulose, hemicellulose, and lignin. These materials can be collected and subjected to pre-treatment processes, such as alkaline or acid treatment, to separate the cellulose. After purification, the cellulose is mechanically or chemically broken down into nanocellulose. This method is particularly effective for converting large volumes of waste into valuable materials while reducing landfill use and environmental pollution. Producing nanocellulose using wastewater and digestate. Organic waste from food processing, livestock manure, or sewage can be treated in anaerobic digesters, which produce biogas, mainly methane, and digestate, a nutrient-rich slurry. The digestate can support the growth of algae, fungi, or bacteria, which in turn produce biomass containing cellulose. For example, algae grown in wastewater can fix CO2 while absorbing nutrients from the waste, generating biomass that can be converted into nanocellulose. This process integrates pollution control with material production. Processing the biomass into nanocellulose. Once cellulose is harvested from any of the above pathways, it must be processed into nanocellulose. The key techniques include mechanical fibrillation using high-pressure homogenizers, microfluidizers, or grinders to break down cellulose fibers into nanoscale dimensions. Acid hydrolysis, especially with sulfuric acid, to produce highly crystalline cellulose nanocrystals, CNCs. Enzymatic hydrolysis for a milder, environmentally friendly alternative that breaks down amorphous cellulose. Chemical oxidation, such as tempo-mediated oxidation, to improve dispersibility and functionality of the resulting nanocellulose. These processes yield different forms of nanocellulose, including cellulose nanofibrils, CNFs, and cellulose nanocrystals, CNCs, which can be tailored for specific applications in packaging, construction, electronics, medicine, and more. Environmental and industrial benefits. Producing nanocellulose from CO2, methane, and waste streams offers multiple sustainability benefits. Reduces greenhouse gas emissions by utilizing pollutants as raw materials. Diverts waste from landfills and turns it into high-value materials. Replaces fossil-derived plastics and synthetic materials with biodegradable, renewable alternatives. Supports a circular bioeconomy, where waste becomes a resource for new production. This approach aligns with climate action, pollution reduction, and sustainable development goals across sectors such as packaging, textiles, agriculture, construction, energy, and healthcare. Nanocellulose can be produced sustainably by integrating carbon capture, microbial or algal growth, and waste valorization systems. Through biological and chemical processes, CO2 and methane can be transformed into cellulose-rich biomass, and organic waste can be purified to extract cellulose. These raw materials are then refined into nanocellulose using mechanical, enzymatic, or chemical treatments. This method not only creates high-performance, eco-friendly materials, but also contributes to solving major environmental challenges by turning pollution and waste into a sustainable resource. What are the best energy technologies can nanocellulose achieve? Nanocellulose enables cutting-edge energy technologies that are more sustainable, lighter, more efficient, and biodegradable compared to conventional materials. Its unique properties, such as high surface area, strength, flexibility, tunable chemistry, and eco-friendliness, make it an excellent platform for a wide range of advanced green energy solutions. A comprehensive explanation of the best energy technologies nanocellulose can achieve and how they contribute to sustainability. High-performance batteries and supercapacitors. Technologies. Nanocellulose-based electrolytes, separators, and electrode supports. Flexible, paper-based batteries and supercapacitors. Benefits. Lightweight and flexible energy storage devices. Non-toxic and biodegradable components. Nanocellulose enhances ion transport, mechanical strength, and electrolyte retention. Compatible with lithium-ion, sodium-ion, zinc-ion, and next-gen batteries. Reduces use of fossil-based polymers and synthetic binders. Enables recyclable, eco-friendly battery designs. Flexible and printed solar cells. Technologies. Nanocellulose used as substrate or transparent film in organic and perovskite solar cells. Printable solar panels on biodegradable surfaces. Benefits: ultralight, flexible, and foldable solar technologies. Can be integrated into clothing, backpacks, building materials. Enhanced transparency and moisture barrier properties. Replaces petroleum-based plastic substrates. Reduces electronic waste and enables low-energy solar manufacturing. Green hydrogen production and fuel cells. Technologies: nanocellulose membranes in electrolyzers and proton exchange membrane fuel cells. Catalyst support structures for water splitting. Benefits: biodegradable, low-cost alternatives to naphthalene and other synthetic membranes. NanoCellulose supports high proton conductivity and mechanical stability. Supports clean hydrogen production and usage. Enables hydrogen energy systems that are cleaner and safer. Materials are renewable and reduce toxic waste. Thermal energy storage and insulation. Technologies: nanocellulose-based aerogels and composites for thermal energy storage. Used in solar thermal collectors and heat-regulating building systems. Benefits: extremely low thermal conductivity. Lightweight, fire-resistant insulation for buildings and energy systems. Reduces energy demand in buildings. Replaces synthetic foam insulation with biodegradable, low-impact alternatives. Energy harvesting devices. Technologies: nanocellulose in piezoelectric, triboelectric, and bioelectronic generators. Energy harvesting for movement, vibrations, and body heat. Benefits: can be used in wearables, self-powered sensors, and remote devices. Safe for skin contact and fully compostable. Enables decentralized low-power devices for smart grids, health, and agriculture. Next-gen structural energy materials, structural batteries. Technologies: nanocellulose composites used in load-bearing battery components. Materials serve as both structural support and energy storage. Benefits: integrates batteries into walls, vehicle bodies, drones, and devices. Reduces weight and complexity of systems. Reduces material use and simplifies recycling. Supports circular design in vehicles and smart infrastructure. Biorefinery integration and energy co-production. Technologies: nanocellulose is a co-product in biomass-to-energy systems, e.g., biogas plants, pyrolysis. Can be extracted from agricultural or industrial waste streams used in energy production. Benefits: increases total value and efficiency of biomass utilization. Energy plus material co-production in circular bioeconomies. Converts waste into clean energy and useful materials. Supports carbon-negative manufacturing processes. Nanocellulose enables a new generation of clean, decentralized, and biodegradable energy technologies. It replaces synthetic polymers and non-renewable components with renewable, carbon-neutral, and biodegradable alternatives. From printed solar panels to eco-batteries and hydrogen membranes, nanocellulose provides the foundation for sustainable energy systems that align with global climate and environmental goals.